Okay, welcome to the micro engineering course. Today we start here a two cavity klystron. We learn about a klystron. Then there are the two types of a klystron. There we will learn a two cavity klystron, then multi cavity klystron, and again another klystron is that is about a reflex klystron that we learn here. So klystron, it is to be used as amplifier here. So we can say that a two cavity klystron amplifier, or we can say that a klystron amplifier. If it is a Klystron amplifier, it can be a two cavity or it can be a multi cavity. So here we talk about a Klystron first, a two cavity Klystron first, and then we see a multi cavity Klystron, and after that we talk about that a reflex Klystron. So now in a two cavity Klystron, so in which a reentrant cavity is used. What do you mean by reentrant cavities? Reentrant cavities that will work at a high frequency. So if you consider a general cavity resonator. So means at a low frequency, if you consider that a cavity resonator, that cavity resonator can be represented by a lumped circuit here. That is about a lumped resonator circuit. But at that particular frequency, at a low frequency, so in that case, what happens? That inductances and capacitances at that particular frequency will be reduced, and it will be minimum in order to maintain the resonance at the operating frequency. So now that inductance, if it is reduced to a minimum and a capacitance again it is reducing, so what happen here? The in the cavity, the cavity is not able to work at a micro frequency. So the reentrant cavities are designed in such a way that they are able to work at a micro frequency. So there are the various reentrant cavities. We supposed to be consider reentrant cavities is likewise here. One structure we supposed to say that reentrant cavity is called as a coaxial cavity now. Okay, this one is about a coaxial cavity. Then we say that radial cavity. Okay, so this one is about radial cavity here. Then we say that a tunable cavity. This one is about a tunable cavity. Then a toroidal cavity. Instead of a rectangular, there will be a circular shape. That is about a. This one is called as a tunable cavity, and another one is about a butterfly cavity. Now these are about the various cavities. So here in some books they are using a coaxial cavity, or some books they are using a radial cavity. But the explanation of the klystron amplifier or two cavity klystron is same even if we are using this particular cavity. So for that purpose we should know that what is the characteristics impedance for this particular cavity, and then we need to proceed using the cavity there. But if you go here to talk about that cavity there, so cavity has some particular length. This one is about, we say, this one is about a total length. Okay, so for this given particular cavity, if supposed to be used this type of a cavities, so this one is about total length. So in general, we supposed to say that this, because this one is a gap, so this one is nothing but the length of the cavity, and this one is nothing but a gap here. Okay, so that can say that's about a d here. So that L is the nothing but the length of the cavity, and D is nothing but the gap of the cavity there. Okay. Now we consider here for this two cavity klystron, how this cavity is to be used. In general, if you draw a coaxial cable, likewise, this one is about coaxial cable. For this coaxial cable, it will be looks like that. And then cavity is nothing but what? Here internally, using a different paint here. It will be looks like cavity. Okay, so now this one is a cross section. If you cut this one, we will get the a cavity. So this is about a this particular portion is connected here. This one portion is connected here, and this one is nothing but the gap. Okay, so likewise, this one is about a cavity. So now we consider now a two cavity klystron. So what are the components in the two cavity klystron? Main component is about a cathode, and then another component is about a collector. And then this particular klystron is used to amplify the signal. That amplification of signal is takes place because of that velocity modulation takes place in the klystron, as well as the amplitude modulation takes place in the klystron. Now, what do you mean by the velocity modulation? Velocity modulation means what? The electrons interacted with a field, external field, or you can say that a microwave field there. When that electron interacted with a microwave field, so then electron will accelerate it or decelerate it, and they form the bunch of the electron. And that process of the acceleration and deceleration of the electron is called as the velocity modulation. Because acceleration and deceleration means what? Electron get the energy, so that's why it will move faster, or electron will move slower there. So that is about the acceleration or deceleration of the electron. Acceleration means electron will get the energy from the field, so that it will move far fast. Electron will reduces the speed because of they are interacting with the microwave field in a negative half cycle. So that's why they will reduces their speed there. That is nothing but a deceleration, and that process is called as a velocity modulation. Here, that electron accelerating and decelerating, and that particular occur in a interaction region. Okay, that interaction region is nothing but inside the amplifier is from inside the two cavity Klystron amplifier. There is a cathode we supposed to be considered. This one is about a cathode here. Okay, this one is about a cathode here. Okay, likewise, you can see that. Okay, so this one is about a cathode here. Then it emits the electron there. Then there will be a anode. This one is a anode, and then we supposed to be consider that there will be a cavity. Okay, this one is called as a buncher cavity. Then another cavity we have, that cavity is called as a catcher. And then we supposed to be consider that at the end it will be a collector. Now the electrons are moving through this cathode. It emits electrons are emits from the cathode. Then it will reach to this cavity. It's nothing but the electrons are moving. Where it will reach, this cavity is called as a buncher cavity. I'll say that buncher cavity. And this one is about a catcher cavity. Okay. Now, what happened here? This one is the cathode, this one is the anode. Here, we're supposed to provide the input, that is the RF field here. we supposed to say that RF field here, and here we are getting the output from this tube. That is about a RF output. This one is about a RF input. This one is about a RF output. And then this one is about a collector. So collector is nothing but what we have a, or whatever the electrons are there, that will be collected at the a collector there. Now what are the voltages? Okay, generally we say that we apply the high DC beam voltage, okay, to this particular cathode. Then there will be anode. This one is about connected to the cavity. Okay, so we can supposed to be say that likewise we supposed to be consider that anode is connected here. Likewise, we supposed to consider that is about the anode here. Okay, so forget about this. We'll talk about how this interaction will be takes place. Now, electrons are moving. Electrons are moving from this cathode to this a puncture cavity. So now when it will reaches to this particular cavity, so electron has some particular velocity. Okay, electron is having some velocity. They are moving from the cathode and they will reach to this puncture cavity. Now here RF input is applied. Now that RF input is available at the mouth of this particular cavity. This one is nothing but a spacing. That is about a spacing. That is about a D here. So now when those electrons are interacted with this RF field, so then that electrons will form the bunches. So then they will form the bunches likewise. They will form the bunches likewise and they will move forward. Whatever the bunches of the electrons are there, they will move forward and then that bunches will be reached here. Now these are the bunches. Now because of that interaction with this RF field, so electron will form the bunches. Okay, now how that bunches form? Because of that acceleration of the electron and deceleration of the electron. We'll see that. Okay, and then once the electrons will form the bunches, so then they will move further toward the another cavity that is called as the catcher cavity. Now because of that interaction with this RF field, they form the bunches and electron will raise their energy, and that energy is called as the kinetic energy. So electron will get the kinetic energy from this field and then they will reach to the catcher cavity and then electron will give up their kinetic energy to the RF field. So then we'll get the RF output will be amplified. Okay, so now here the electron will give up the energy to this catcher cavity and then those bunches will give up the energy to the RF field. Then they will move toward the collector and it will be collected here. Okay, so it will be collected at the end here. So now that is about a two cavity crystal. Now the process of how that electrons are forming the bunches, and that is called as a applicate diagram or a bunching process. Now in a bunching process, generally what happens that acceleration of the electrons and deceleration of the electrons will be takes place. Now how it happens? So generally, so this one is about a what we can say that a gap of whatever the gap voltage. Okay, this one is about a gap voltage across this particular cavity. So gap voltage is nothing but a whatever the RF signal we supposed to be considered. So now we'll see here this one is about we can say that this one is about generally we supposed to be consider that a gap voltage. Likewise. So now the electron those who are supposed to be this one is about a negative half cycle we consider. This one there is about a transition of this cycle and here we have a maximum peak. Now this one is the gap voltage. Now just tilt this one. So likewise, how it will be looks like here at this particular case here. So your circuit will be this this gap voltage will be looks like positive half cycle and negative half cycle. Okay, this positive and negative line here. So now come here. So what happens? So electrons are interacting. So now electrons are coming from this line. These are the electrons. This one. These are the electrons. This one is the electron. So likewise. So when electrons will reach at this particular point, okay, where we have this gap here, so electron will accelerate or decelerate there. Now those electrons are moving in this negative half cycle. So they will reduces their speed. And here those electrons are moving in the positive half cycle, they will move fast. So now this one is about a time taken by the electron from moving from the negative half cycle or time taken by this electron from the positive half cycle. It will be different here. Okay, the velocity of that electron, those moving in the negative half cycle, that will be slow as compared to the velocity of the electron, those who are moving in the positive half cycle. So this one is a faster electron and this one is about a slower electron. Now the interaction of the electrons at this cycle, okay, when their transition from the negative to the positive changes here, so in that case, that electrons having the a constant speed. Okay, velocity of the electron will be a constant here, but the velocity will be slow and velocity will be fast. So then at some particular point they will form the bunches here. So that is called as a bunches formation. Okay, that is called as a bunching diagram or we say a applicate diagram. So now from this we find out what at what particular place that bunches formation will be takes place. Okay, and this one is nothing but a gap voltage. This one is about a gap voltage. This one here is about a gap voltage. So now the electron passes through this particular gap voltage. Okay, electrons are passing through the gap voltage. If the gap voltage is a positive, so in that case, electrons will accelerate. Means electrons will accelerate means what? The speed of the electron, that velocity of the electron will be increased. Okay, velocity of the electron. That is about the velocity. Electron moving from the cathode, it has some velocity. And that velocity is depending upon that how much is the beam voltage we apply at the cathode. This one is about a cathode. So that velocity of the electron, it will be increased, further increased if they are moving through this gap voltage, positive gap voltage, and then they will reach at that particular point and then they form the bunches. So those electrons moving through this particular positive half cycle, they increase their velocity, and those electrons moving in the negative half cycle, they will decrease their velocity, and at some particular point they will reach and they will form the bunches. Okay, that is about it. Where we say is supposed to be a point, and that is nothing but called as a bunches. So now that bunches are passing through this buncher cavity. Now this is about a formation of the bunches takes place because of that gap voltage of a cavity. And that gap voltage, how it will come? Because there will be RF voltage we are applying. That is the micro signal we are applying. So that micro signal supposed to be amplified that we are applying here. And then because of that signal, a bunches formation takes place. And then that bunches are moved toward the another cavity. That cavity is called as a catcher cavity. Okay, now this one is called as a catcher cavity. Now velocity of that electrons is changes here because of that how because of that electrons are passing through this buncher gap or a buncher cavity. So that's why that velocity of that electrons will be increased or a decrease. So that process is called as a velocity modulation. And that velocity of that electrons are move changes, acceleration or deceleration occur because of RF field. Means your electrons are interacted with the RF field. Okay, when electrons are interacted with the RF field, so then they they will change their velocity. Means velocity of that electron will be changes. Means acceleration, that is about a faster electron. Deceleration, that is about a slower electron. So that is called as a, what you can say that at a positive half cycle, velocity of the electron is changes. Means electrons are accelerated. So means electrons will move fast. At the negative half cycle, electrons are decelerated. Means that decelerated means that velocity of that electron will be reduced, and that all this process will be occur here in this particular puncture cavity gap. and that process is called as a velocity modeling. Okay, that process is called as a velocity modeling. Now then, electron bunches are moving from this buncher cavity to the catcher cavity. Now this one is about a gap between the buncher cavity and a catcher cavity, and that gap is called as a drift space. That gap between the buncher cavity and a catcher cavity is called as a drift space. So we need to find out, or we need to consider that space in between the buncher cavity and catcher cavity in such a way that they will reach to the catcher cavity with a bunches formation. That electrons to be reached at the catcher cavity with the formation of a bunch. If that catcher cavity will be nearby to this buncher cavity, so bunches formation will not be takes place earlier toward, okay, before the catcher cavity. So that's why that gap between this buncher cavity and catcher cavity is to be changes. Okay, it is to be vary, so that we'll get that a higher amplification. Now then, what happen here? That bunches formation takes means electron are get the energy from this field there. Okay, then they are moving toward this particular drift space there. Then here is the catcher cavity. Then the electron will reach to the catcher cavity, or this is nothing but a catcher gap, and then electron will provide their energy to this RF field. Okay, so then what happened? The bunches provide the energy to the this particular cavity. So that's why it's called as a catcher cavity. So means it catches that particular velocity modulated bunches. It catches the velocity modulated bunches there. So that's why that cavity is called as a catcher cavity. And well, that particular cavity will reach that catcher cavity will here will give up the energy, that is the output, that is the RF output, that will be amplified. So here the variation in terms of a current takes place inside the catcher cavity because they will give up the energy to this RF field, and that process is called as a current modulation. So here the velocity modulation bunches provide isolated and dissociated. They will give up the energy. Okay, that process is called a current modulation. So that is about a two cavity klystron. In a two cavity klystron, we are supposed to be consider that there are the two cavities. One cavity is called as a buncher cavity, and that buncher cavity is used to form the bunches of the electron. Okay, that bunches of the electrons will be formed. Okay, that bunches formed because of that positive half cycle and negative half cycle of that RF field, and that process of that acceleration or the deceleration of the electron, which in that process of the velocity variation of the electron, that process is called as a velocity modulation. And because of that velocity modulation, that bunches of the electrons will form, and then bunch electrons will move forward toward the another cavity, and that cavity is called as a catcher cavity. And here, because of that bunches formation, so the density of the electrons in the catcher cavity varies according to the cyclic time. Okay, because here we say that the velocity modulation there, and then the bunches formations are take place, and the density of the electron in the catcher cavity varies according to the cyclically with respect to time. Then here we have the catcher cavity. Then electron beam, here we supposed to consider that a modulated electron beam is modulated by with a RF field here. And that electron beam is modulated, means modulation here, that velocity modulated here. Why it is that modulated? Because of that RF field. Means this one is about a DC beam and this one is about a RF field. So that RF field contains a AC component here. Okay, that RF field is contained the AC component. So that's why what we can say that it is about a current modulated. Okay, so we need supposed to find out the place here. A maximum bunching occurs approximately at the midway between the second cavity, midway between the puncture cavity and a catcher cavity. Okay, so this is one particular place here. And that particular uh, region is called as a drift region. And then what happens? That kinetic energy of the electron beam is transferred to the catcher cavity here, and then that will result in the amplification of the signal. So means that energy in the catcher cavity, that is depending upon that electron beam, or we can say that it will be depending upon that whatever the bunches formation takes. Once that energy give up to this catcher cavity, then velocity of that electron or velocity of those bunches will be reduced, and then it will be move slowly toward the collector. Now here it is a faster in this drift phase, that bunches will be move faster, but when they will give up the energy to the catcher cavity, then it will move slowly, and then it will be collected at the a collector. So now that is a two cavity crystal. So now we need to talk about that. What happened to the velocity modulations, and what how your output of this how your that Klystron will produce as a higher value of a output there. So that's why we need to learn here first of all what will be the process of the velocity modulation here, and what will be the output here. So then we will talk about first for a two cavity Klystron what will be the efficiency here. That efficiency is depending upon that a power output. So generally a two cavity Klystron will produce a power output. It is depending upon that the operating frequency. Suppose we can generally consider that efficiency is nothing but a approximately it is about a 40%, and a power output if supposed to be, if you consider that a continuous power CW power, then in that case the average power is up to a 500 k. Okay, and if you consider supposed to be a pulse power, then a average power output will be a 30 megawatt, and that will be at a 10 gigahertz, and a power gain is about a 30 dB. That is about a power gain. Okay, so now it everything that for particular cavity, it is depending upon that what will be the operating frequency of the Klystron, that cavity there, or a Klystron there. So how what will be the velocity of the electron? So generally we say that a cathode emits the electron. Okay, cathode emits the electron because we supposed to apply the high DC beam voltage to this cathode. So means we say that this is about a DC voltage we apply to this cathode. So then it will provide the large number of electrons, and that velocity of this electron, it is depending upon that how much is the DC beam voltage, or how much is the DC voltage we apply to this a cathode there. So that's why the velocity of the electron, it is depending upon the DC voltage. So now this one is about the a velocity of the electron there is equal to under root of twice E capital V0 by M. Okay. So now here we supposed to be consider that a beam voltage, that is about a capital V0 is nothing but a DC beam voltage. Okay, that is about a that capital M we capital V0 is nothing but a DC beam voltage. Now this particular factor, that is about the electron energy and their mass. Okay, this particular factor E by M, it is nothing but a constant here. So what is the value of this particular constant? Generally we supposed to write the equation. If you put the values of this E and M here, okay, what will be the charge and what will be the value of M here? Okay, so in that case we will get the velocity of this particular electron is equal to 0.593 under root of, one is about a capital V0 into 10 to the power 6. That is about the velocity of the electron there. Then we consider that a micro signal is applying. Micro signal is applying because RF input we say. That a micro signal is supposed to be right here in the form of V1 sine of omega t. Okay, so that is about a V1 sine omega t. Now that is about a micro signal, and that for a micro signal, that is about a RF input we apply. So that for a given signal, that V1 is nothing but the amplitude, and generally we say that a V1 is very less than the DCB voltage. Okay, so whatever the micro signal we apply, that is to be a very less than the V0 there. And then based on this particular signal, at a puncture cavity, this particular puncture cavity, velocity modulation will be takes place. Okay, how velocity modulation takes place? Generally, we supposed to be consider that. So here we supposed to be see that signal now. So now this is about a Vs, and this one is about amplitude, supposed to be a Vn. And for this, okay, so for this, your electron to be propagating at this particular signal there. So what will be the values of this particular puncture grid here? So that gap is nothing but a d here. Generally, we say that for a given particular cavity, this one is about a gap. Okay, so this gap, and this gap is nothing but a d, small d. This gap. Okay, how much is the gap there? That is about a small d there. That is about a for a given particular puncture grid here. And now your electrons are interacting. Okay, they are interacting at a particular time. Generally, we say that interaction takes place at this time will be different, and this time will be different. So time entering, this one is supposed to be T0, and time leaving through this gap is supposed to be a T1 now. So means at this particular time T0, your electrons entering to the bunching cavity, and then it will leaving from the bunching cavity at a time T1. And then that a gap, what is the gap transit angle? That is about a theta g. Okay, this one is about a gap here. That is about a gap. So in that case, for a given particular gap, so there will be a gap transit angle, and that gap transit angle will be a theta g. So from this we find out what will be the average transit time through the puncture gap distance d. Okay, so this one you just remember that value here. Then next is about, that is about a time taken by this bunches formation there. So that's why we can supposed to be right the average transit time, that is nothing but a 2, and that is depending upon that what will be the spacing. Okay, that what will be the spacing or what will be the gap here, and what will be the velocity of the electron, and that is equal to T1 minus T0. T1 is what? Exit time, and T0 is what? Entering time. Okay, T1 is nothing but exit time, and T1, T0 is nothing but the entering time. Because electrons are moving through the bunching cavity at a time T0 and leaving from at the time T1. And that is nothing but a average transit time. That is interaction space in the buncher gap. That is called the average transit time through the buncher gap distance d, and it is depending upon that velocity of the electron. Then the average gap transit time is equal to average gap transit time angle. Okay, average gap transit time angle is equal to, because this one is average transit time. So average gap transit time angle theta g is equal to omega t. or that t is nothing but what? T1 minus T0. Or if you write in terms of this one here, T1 minus T0 is nothing but tau or d by V0. You can say that omega d by V0. Okay, omega d by V0. That is a velocity. D is nothing but a spacing. Then what will be the average micro voltage in that particular puncture gap? And that average micro voltage in that particular puncture gap, it is depending upon that what will be the average transit time voltage, average transit time, as well as the average gap transit time. So we'll write here the equation about that, the average transit time. Okay. So next is about average microwave voltage in the puncture grid. Okay, puncture graph. Okay, the puncture graph. How much is the average voltage? That average voltage is nothing but what? Whatever the signal, micro signal, we supposed to be considered, and that is with respect to how much is the time there, transit time. Okay, how much is the transit time? The transit time we supposed to be considered that from the T0 to a T1, from the T0 to T1, and we supposed to be considered that sine of V1 sine of omega t dt. So now if you solve this one for this omega t0 and omega t1, so we will get that average Vs here is equal to V1 by omega tau into cos of omega t0 minus cos of omega t0 plus omega d by V. Okay, now this one. So now this one is about a cos omega t0 and this one is about omega t0 plus omega d by V0. Now if you consider that a cos A minus cos B, cos A minus cos B. Okay, this one is about what you can say that cos A. Okay, so I'll just consider that, rewrite again, cos A minus B here minus cos of A plus B is equal to twice of sine A to sine B is equal to twice of sine A to sine B. Now we consider that this expression here, okay, and if you solve it for this cos of A and cos of B term, so we'll get that in terms of a sine term. So after solving this, I am going to write directly now. That equation becomes what? A V1 sine of omega d by twice of V0 by omega d by twice of V0 is equal to sine of omega t0 plus omega d by twice of V0. Now consider here, we can earlier we say that omega d, okay, that theta g, we say that earlier we say that theta g is equal to what? Omega d by V0. Means omega d by V0 is nothing but what? We can write here this equation in terms of a theta g. Okay, this one is about a theta g by 2, theta g by 2. Here, this one expressions we have omega t0. This one becomes a theta g by 2. We can write the expression again for this v1 sine of theta g by 2 divided by theta g by 2 into sine of omega t0 plus theta g by 2. Now, this one is about our expression. So, that is about a average micro voltage. Okay, average micro voltage in the puncture cap. Now, then from this equation, if you consider that this side of theta g by 2 and this theta g of 2, or we can say that this particular term, this particular sine of omega d by twice v0 and this omega d by twice v0 and this particular factor here it is representing what a average gas transit time here. Okay, that average this one is about a average gap transit angle theta g is average gap transit angle, and from this we will get from this equation this particular factor is called as a beam coupling coefficient of the input cavity gap. So at a puncture cavity, so beam is coupled, so that's why this particular factor is called as a beam coupling coefficient. So we'll rewrite here the expression for the beam coupling coefficient. That beam coupling coefficient is nothing but a bi, beta I. Okay, right here. Okay, that is about a beta I is equal to sine of omega d by twice of v0. That is velocity. D is this d is spacing here. Omega d by twice of v0. Omega d by v0 is nothing but a sine of theta g. Sine of theta g by 2, and this one is about a theta g by 2. So that is about what we can say that a beam coupling coefficient. Okay,